Hello everyone. So I am Lavanya from Department of Computer Science Engineering, Sri Venkateshwara College of Engineering. So today in this video we are going to see Unit 5 Encoder, Decoder, RNN and GRU comes under CS22032 Deep Neural Networks. So let's get started. Next, encoder and decoder RNN. So uh, this architecture is widely used in sequence to sequence problems where we need to convert one sequence into another sequence. A common example is translating a sequence from one language to another. The encoder decoder model consists of two main parts, the encoder RNN and the decoder RNN. These two networks are connected in a front to back structure, meaning the output of the encoder is used as the input for the decoder. First, encoder RNN. Let's start with the encoder. The encoder RNN processes the input sequence step by step. It reads the input one element at a time and updates its internal hidden state at each step. So, if we have an input sequence x1, x2 up to xt, the encoder transforms this sequence into a series of hidden states h1, h2 up to ht. Each hidden state captures information about the input seen so far. As the sequence progresses, the encoder builds a compressed representation of the entire input. In simple terms, the encoder is responsible for understanding and summarizing the input sequence. Decoder RNN. So the decoder takes the information generated by the encoder and uses it to produce the output sequence. It receives the encoder's hidden states or final context representation and starts generating output step by step. So the process can be represented as H1, H2 up to HT, Y1, Y2 up to YT. So here the decoder uses the encoded information hidden states as a context. It generates each input element sequentially. Each output depends on previously generated output as well as encoded input. So the decoder is responsible for producing the final transformed sequence. So the encoder and decoder structure allows the model to first understand the entire input sequence and then generate a meaningful output sequence based on that understanding. So this separation makes it very powerful for tasks where input and output sequence are different. So second one is attention mechanism. So in basic encoder and decoder RNN, the encoder compresses the entire input sequence into a fixed size representation, which is then passed to the decoder. So however, this can become a limitations, especially for long sequences, because important information from earlier time steps may get compressed or lost. To solve this, the attention mechanism was introduced. So attention allows the encoder to focus on specific parts of the input sequence at each time step instead of relying only on single fixed vector. So this means that while generating each output word, the decoder can look back at different parts of the input sentence and decide which parts are more relevant. For example, when translating a sentence, the model does not treat all words equally. Instead, it dynamically assigns importance to different words depending on what it is currently generating. This significantly improves performance, especially for long and complex sequences. So the main idea behind the encoder-decoder architecture can be as encodes first The encoder will understand and encodes the input sequence into meaningful representation. So this is the first step. First, the encoder will understand and encode the input sequence into meaningful representation. So second one is the decoder takes this encoded information and generates the output sequence step by step. So when attention is added, the decoder becomes even more powerful because it can selectively focus on different parts of the input while generating each output. So instead of relying on a single compressed representation, the model uses context-aware dynamic focus. So the applications used are one of the most important application is neural machine translation. So especially in the systems developed between 2014 and 2017. So these models were a major breakthrough in translating text between languages like English, French and many others. So in addition to translation, this architecture has been used for text summarization, speech to text systems and dialogue systems. So it played a crucial role in advancing deep learning for language tasks. So most importantly, the idea of attention became a key stepping stone towards transformer models, which later revolutionized natural language processing by removing recurrence entirely. So this is the architecture for encoder and decoder model, which is used for sequence to sequence task. Encoder, first we look at the encoder on the left. Its job is to process the input sequence represented here by X0 and X1. As each input passes through the RNN cells, the network updates its hidden state H0 H1. This process compresses the entire input sequence into a single context vector which captures the essential meaning of the data. So next one is the decoder. Next, the decoder takes the context vector to begin generating the output. So we see two distinct training strategies here. First one is using prediction and second one is teacher forcing. So using prediction, the model uses its own previous output as the next input, and this is how the model operates during real world inferences. Second one is teacher forcing. During training, we often use teacher forcing where the actual ground truth X2 is fed back into the next RNN cell. This corrects the model's path and significantly speeds up the learning process. So by combining these two components, RNN can effectively translate languages, summarize a text or predict future time series data. So next, this diagram shows an encoder-decoder architecture with an attention mechanism commonly used in tasks like neural machine translations. So let's look at how recurrent neural network handles sequence to sequence tasks. So in this example, we are translating a phrase using an encoder-decoder model enhanced by an attention mechanism. So the encoder left side, on the left we have the encoder. It takes the input sequence here, the words, the S0 and zone S1. Each word passes through a RNN cell producing hidden states H0, H1. These states capture the contextual meaning of the input words. So the attention mechanism in the middle, instead of passing just one final vector to the decoder, we can use an attention mechanism here. This allows the model to look back at all encoder hidden states H00 through H11 and decides which specific parts of the input sequence are most relevant for the current word being generated. Uh, as like that, the decoder right side, it starts with start token. At each step, the decoder RNN H2H3 combines its previous state with the context provided by the attention mechanism to predict the new world. So in this flow, you can see it successfully predicting the output words LAT1 and zone T2. So by using attention, the model avoids the bottleneck problem of traditional RNN, ensuring that even in long sentences, the decoder never loses track of the original input nonsenses. So here is the difference between pixel RNN and diagonal by Lstm. So pixel RNN is an extension of recurrent neural network that allows them to work with two-dimensional data such as images. Instead of processing an image at all at once, pixel RNN treats the image as a sequence of pixels. This means the model generates or predicts pixels one at a time in a specific order, usually following a raster scan pattern. So the image is not seen as a complete grid initially. Instead, it is built gradually where each pixel is predicted based only on the pixels that have already been generated. So this sequential nature ensures that every prediction is conditioned on previously known information, allowing the model to learn probabilistic relationships between pixels. So pixel RNN extends the idea of sequence modeling from text and speech to images by treating pixels as a time-oriented sequence. So whether diagonal by LSTM uh, can be while pixel RNN works well, it can be limited in how much spatial context it captures and if it is only processes pixels in a single direction. To improve this, we use the diagonal bidirectional LSTM. So it introduces a powerful way of scanning the image by using two directional flows. One direction moves from top left to bottom right and other moves from top right to bottom left. By doing this, the model captures information from multiple spatial paths instead of just one sequential path. Each pixel is influenced by a richer set of neighboring pixels, allowing the model to better understand spatial relationships such as edges, shapes, and textures. This dual direction processing significantly improves the model's ability to represent complex image structure. The next topic is pixel RNN. So the main concept of pixel RNN is it is a generative model that applies the idea of recurrent neural network to images which are two-dimensional structures. Normally, RNN are used for sequences like text or speech, but pixel RNN takes a different approach and it treats an image as a sequence of pixels instead of a fixed grid. This means the model does not generate the entire image at once. Instead, it generates the image one pixel at a time following a specific order. The key idea is that every pixel is not dependent. Instead, it is conditioned on all the pixels that already have been generated. So mathematically, pixel RNN models the probability of an image as P of image equal to product of P each pixel to the previous pixel. So this ensures that each pixel is predicted based on the context, just like words in a sentence depend on previous words. Second one is row by row sequential processing. So to apply this idea, pixel RNN converts a 2D image into a 1D sequence. So two-dimensional image to one-dimensional sequence. For an n by n image, the pixels are arranged in a fixed order as x11, x12 up to x1n, x21, x22 up to x2n till xnn. This means the model processes the image row by row, and within each row left to right and each step the model predicts the next pixel based only on the pixels that have already been processed. This sequential ordering is very important because it prevents the model from cheating by looking at future pixel. Third one is dependency structure. So when predicting a pixel at position I, j, the model is only allowed to use pixels to the left in the same row and pixels from the rows above. So the prediction looks like P of xij. So all the pixels before it in faster scan order. So this ensures that the model builds the image in a natural and consistent way. For example, if the model is generating a face, earlier pixels might define the shape of the head. Later, pixels then refine details like eyes, nose and texture. This progressive construction allows the model to maintain spatial coherence across the image. So fourth one, why pixel RNN is powerful. So pixel RNN is useful because it learns a probabilistic model of images. It generates images pixel by pixel in a structured way. It captures local and global dependencies in images, and it produces highly consistent and realistic outputs. So it is also computationally expensive because it processes pixels sequentially, which makes it slower compared to parallel models like CNN based generators. The next topic is diagonal bidirectional Lstm. So it is used to improve how images are modeled during recurrent neural network. So in standard pixel RNN, we process pixels row by row. However, this approach can sometimes limit how much spatial context the model can capture at each step. To improve this, Pixel RNN introduces a diagonal bidirectional LSTM which allows the model to capture dependencies in multiple directions more effectively. Instead of only moving left to right or top to bottom, the image is processed along diagonal directions, which helps the model capture richer spatial relationship between pixels. So second one, first LSTM, top to left, bottom to right direction. So the first LSTM processes the image in a diagonal flow from top left to bottom right. For each pixel at position ij, the model does not rely on only on the current pixel. Instead, it depends on information coming from two key directions. From the pixel above, that is I minus 1 to j, from the pixel to the left, that is I comma j minus 1. These dependencies include both hidden state h, self state c. So the pixel x ij is influenced by h I minus 1 j, c I minus 1 j, top context, h I comma j minus 1, c I comma j minus 1, left context. So this means the model builds understanding using both vertical and horizontal past information simultaneously. So by combining these two sources, the LSTM can effectively capture local spatial structure in the image. So next one is second LSTM, top right, bottom left direction. So now to make the model even more powerful, a second LSTM is introduced. This second LSTM processes the image in the opposite diagonal direction from top right to bottom left. Instead of only using left and top information, this LSTM captures right side context as top right diagonal context. So for each pixel x of I comma j, it learns from the future spatial structure relative to the first direction. So this allows the model to understand patterns that might be missed when processing in only one direction. So why these two directions matters? By combining both diagonal directions, the model gains a complete spatial understanding of the image. The first LSTM captures structure from top left to bottom right. The second LSTM captures structure from top right to bottom left. So together they ensure that each pixel is influenced by a rich set of surrounding pixels, improving image coherence and quality. So the main idea behind the diagonal BILSTM is instead of thinking in rows or columns, the model thinks in diagonal flows of information which naturally combine both vertical and horizontal dependencies. This helps pixel RNN to capture long-range spatial dependencies and to improve image generation quality and to produce more realistic and structured images. So next in bidirectional LSTM is visualization. So visualization of grid processing. So to understand diagonal bi-LSTM, the first imagine an image not as a picture. So but as a 2D grid of pixels where each pixel must be generated one by one. Now instead of processing this grid only row by row, Pixel RNN uses a smarter strategy, diagonal traversal. Think of the image being scanned in two simultaneous diagonal waves. One wave moves from top left to bottom right and another wave moves from top right to bottom left. This diagonal processing is powerful because it naturally combines both horizontal structure, left to right relationship, and vertical structure, top to bottom relationship. So now let's focus on single pixel at a position I comma j. So when predicting this pixel, the model is only allowed to use information that has already been computed. So instead of looking forward, it only looks at the pixel above it, up arrow, like I minus 1 comma j. So the pixel to the left I comma j minus 1. So these two dependencies are critical because they represent the entire causal history in a raster scan system. Now here is where bidirectional LSTM becomes powerful. Instead of using a single directional flow, we now have two LSTM streams running in opposite diagonal directions, meaning every pixel is influenced by two complementary contexts. One from the left top propagation and one from the right top propagation. So effectively, each pixel is not just built from one history, but from two structured histories merged together. So this creates a much richer understanding of spatial structure inside the image. Why diagonal bi-LSTM works so well? The main problem in image generation is not just predicting pixel, it is maintaining global coherence. For example, eyes must align properly on the face, edges must stay continuous, and textures must remain consistent across regions. A simple row-based RNN struggles because it only sees a narrow context. But bidirectional LSTM solves this by spreading information in two diagonal directions. So it allowing each pixel to receive multidirectional spatial context and to ensuring both local and long range dependencies are captured. So instead of a chain of dependencies, the image becomes a network of contextual flows where each pixel is informed by a richer neighborhood. This is why pixel RNN with diagonal by Lstm produces sharper images, and it is more structured, gives more structured outputs, and it gives a better global consistency. So next one is connection to encoder and decoder RNN. So stepping back, let's connect this idea with another important architecture, encoder RNN, encoder decoder RNN. At a high level, encoder decoder models are designed for sequence to sequence transformation tasks. So in this, the encoder takes the input sequence like x1, x2 up to xt, and it processes them step by step and compresses the information into the hidden states h1, h2 and up to ht. So this means the encoder is responsible for understanding the input and building a meaningful internal representation. As like that, decoder takes the encoded information and generates y1, y2 up to yt, and it produces outputs step by step where each output depends on encoded text. So previously text with the previously generated output. So the decoder is responsible for getting a new sequence. So by using this architecture, they separate the encoder and decoder in different sequences. So real world application for this is a neural machine translation. Input is an English sentence and output will be the French sentence. So the encoder reads the English sentence and builds the meaning representation. The decoder uses the representation to generate the French translation word by word. So next important topic is long short term memory, LSTM. Um, So it is a special type of RNN designed to overcome one of the biggest limitations of a standard RNN, the vanishing gradient problem. It can be recovered by the LSTM. So in standard RNN, when big sequences become very long, the model struggles to learn long-term relationship because the gradient either becomes too small or too unstable as it is back propagated through time. To solve this, LSTM introduces a more powerful memory mechanism that allows the network to retain important information for long periods of time while forgetting irrelevant details. Key features of LSTM. First one is gated memory structure. So LSTM uses a unique structure called gates which control the flow of information through the network. Among these, the most important is the forget gate. The forget gate decides what information should be kept and what information should be removed from memory. This selective memory mechanism allows the model to maintain only useful information over long sequences. Second one is stable gradient flow. One of the most important advantage of LSTM is that it prevents backpropagated errors from vanishing or exploding. In standard RNN, gradients become weaker as they move backward through time. But in LSTM, the internal structure allows gradients to flow more effectively, making learning stable even for long sequences. This means the model can learn long-range dependencies without losing information during training. Third one is long-term memory capability. So LSTM are specifically designed to handle tasks where important information may be separated by hundreds or even thousands of time steps. For example, a word in a sequence may depend on another word much earlier. A pattern in time series data may depend on events far in the past. LSTM can effectively in the past. So LSTM can effectively remember such long distance relationships. So fourth one is ability to handle long delays. In many real world sequences, there is a delay between cause and effect. So LSTM is capable of learning these long delays, meaning it can connect earlier events with outcomes that happen much later in the sequence. This makes it extremely powerful for tasks like language modeling and speech processing. Then next one is handling mixed frequency signals. LSTM is also effective when dealing with signals that contain both low frequency patterns, slow long-term trends, high frequency patterns, fast short-term changes. Because of its memory structure, it can balance both types of information and learn meaningful representation from complex signals. So gates in LSTM, first one is forget gate. So forget gate plays a important role in managing the memory of the network over long sequence. Actually, there are three gates in LSTM relates which controls the information flow through a sequence. First one is the input gate, and second one is the forget gate, and third one is the output gate. So input gate is the gatekeeper. It controls exactly what new information is allowed to enter the system's memory. And second one is the forget gate. So it plays an important role in managing the memory. So its main job is to decide which information from the previous memory should be retained and which should be discarded. So this is extremely important because not all past information is useful for future predictions. Some information becomes irrelevant, and as the sequence progresses, and keeping it can actually harm the model's performance. So the forget gate helps solve this by assigning a value between 0 and 1 to each piece of information. Just like a value which is close to 1 means keep this information. So if the value is close to 0 means forget this information. So why it is used is it is essential because it allows the LSTM to maintain a clean and relevant memory state over long sequences. So without it, the model would either store too much unnecessary information or lose important long-term dependencies. So by selectively forgetting irrelevant data, the LSTM ensures that only meaningful information is carried forward through the time. And the third one is the output gate. This determines which parts of the stored memory are actually needed for the final output at that specific step. So altogether, these three gates allows the model to maintain and update its memory over very long sequences. So this diagram shows how an LSTM cell works internally. At each time step t, the LSTM receives three inputs, the current input xt and previous hidden state ht minus 1 and the previous cell state ct minus 1. The cell state shown running horizontally across the top acts like a long-term memory. It carries information forward with only minor modifications, which helps to preserve important context over time. Step 1. Forget gate. The first operation is the forget gate labeled FT. So this gate decides what information from the previous cell state should be kept or removed. It takes xt and ht minus 1 as inputs, passes them through a sigmoid function and produces values between 0 and 1. A value close to 0 means forget this information, while a value close to 1 means keep it. This gate is then multiplied element wise with the previous cell state ct minus 1. So it is effectively filtering out unnecessary information. Step 2. Input gate and candidate values. Next, we determine what new information should be added to the memory. This happens in two parts. First, the input gate uh, IT again uses a sigmoid function to decide which values to update. Second, a candidate cell state is created using a tanh function producing values between -1 and 1. These candidate values represent new information that could be added to memory. The input gate then controls how much of this candidate information is actually used. Step 3. Updating the cell state. Now we combine the previous steps to update the cell state. The old cell state, after being filtered by the forget gate, is added to the new candidate values scaled by the input gate. This gives us the new cell state CT. So, in simple terms, we forget some old information and add some new relevant information. Step 4. Output gate and hidden state. Finally, we compute the output gate OT. This gate decides what part of the updated cell state should be exposed as the hidden state. First, the new cell state is passed through a tanh function to squash its values. Then, it is multiplied by the output gate. The result is the new hidden state HT. This hidden state serves two purposes. It is passed to the next time step and it is also used to produce the output OT. So the final flow, at the end of this process, both the updated hidden state HT and the updated cell state CT are passed forward to the next time step. This entire sequence repeats for each element in the input sequence. The key strength of LSTMs lies in three gates. They allow the model to selectively remember or forget information, making it much better at capturing long-term dependencies compared to standard recurrent networks. Next topic is deep LSTM. So a deep LSTM is formed when we stack multiple LSTM layers on top of each other. Instead of using single LSTM layer, the output of one LSTM layer is passed as the input to the next LSTM layer. This creates a deep hierarchical structure for processing sequential data. Each layer in this stack does not learn the same type of information. Instead, each layer specializes in learning different levels of temporal patterns. Lower layers capture simple short-term patterns. Higher layer captures more abstract long-term dependencies. This layered learning makes the model significantly more powerful. Second one, learning hierarchical temporal futures. So one of the key advantage of deep LSTM is that it can learn hierarchical temporal representation. This means the model does not just memorize the sequences. It learns structured patterns across time. For example, in language data, lower layers may learn grammar or local word relationships. Higher layers may learn sentence level meaning or context. This hierarchical understanding allows deep LSTM to perform much better on complex sequence tasks. So, advantages over traditional models. Deep LSTM provides significant improvements when compared to older sequence models like hidden Markov models and simple RNNs. So, context sensitive learning. So, this can understand context sensitive patterns the interpretation of data depends heavily on surrounding context. This is something traditional models struggle with. So next one is superior to hidden Markov model and earlier RNN. When compared to these models, LSTM do not rely on strict probabilistic assumptions like HNM. They can handle long range dependencies much more effectively. So they reduce issues like vanishing gradients that affect early RNN. Next one is long-term dependency learning. So one of the strongest advantages is the ability to learn relationships across long sequences. Deep LSTM can connect events that are far apart in time, which is essential in tasks like language modeling, speech recognition, time series forecasting. Next one is problem specific adaptation. So another important feature of LSTM based architecture is flexibility. So LSTM structures are not fixed. They can be modified, customized or evolved depending on the problem. This means gates can be adjusted, layers can be stacked differently, hybrid architectures can be created, and this adaptively makes LSTM a powerful tool for a wide range of sequence processing problems. So next important topic is gated recurrent unit. So it was introduced in 2014 as a simplified alternative to the long short term memory network, and the main idea behind this was to achieve similar performance to LSTM but with a simpler and more efficient structure. So the main features of GRU are GRU is designed to reduce complexity while still preserving the ability to learn long-term dependencies in sequence data. So fewer parameters than LSTM. So one of the biggest advantage is it has a fewer parameters than LSTM. So it makes it faster to train and less computationally expensive and more efficient in resource limited environments. Because of its simpler architecture, GRU is often preferred when computational efficiency is important. No output gate. Unlike LSTM, GRU does not have a sequence separate output gate. So this reduces the number of internal components while still allowing the model to control information flow effectively. Then next one is update gate. This is a combined functionality. Instead of having separate input and forget gates like LSTM, GRU, LSTM, it combines their functionality into a single component called the update gate. The update gate decides how much past information should be kept, how much new information should be added, and this unified mechanism simplifies the architecture while still maintaining strong memory control. Next one is efficient sequential modeling. So despite being similar, GRU is still very powerful. So it can effectively model sequential data while requiring less computation, making it suitable for real-time applications, mobile or edge devices, large-scale sequence processing tasks. So next one is performance comparison. So GRU performs very similar to LSTM across many tasks. It has shown strong performance in areas such as polyphonic music modeling, speech signal modeling, general sequence prediction tasks, So in real world applications, there is no significant performance difference between GRU and LSTM. So this makes GRU an attractive alternative when efficiency is a priority. So this image illustrates the architecture of the gated recurrent unit, a type of recurrent neural network designed to efficiently process sequential data while avoiding common training issues like the vanishing gradient problem. So this diagram shows the internal structure of a gated recurrent unit, and here the overall flow which defines first the green circle xt is the current input at a time step t. For example, the current word in a sentence, and ht minus 1 blue box which represents the hidden state from the previous step, basically the network's memory of everything it has been seen so far. And the red circle ot is the output at the current step, and ht central blue unit, it combines past memory and current input to produce a new refined memory state to pass forward. And inside the GRU unit, the two key gates controls the flow of information. So first one is reset gate and second one is update gate. So reset gate which determines how much of the past memory to forget or reset. If RT is near to 0, the model ignores the past and focuses primarily on the new input. In update gate ZT, this acts like a filter which deciding how much of previous hidden states ht-1 to keep and how much of the new candidate information to add. Then next one is TANH activation. So we use TANH layer to create a candidate hidden state. It blends the current input with the reset version of our past memory. So by using only 2 gates instead of 3 found in LSTMs, the GRU is more efficient and uses less memory and often trains faster while achieving comparable performance. So it is widely used today in real applications like Siri, Google Translate, and stock market forecasting, etc. So these are the key components of GRU. First one is update gate. So the update gate and the reset gate, these two gates control how information flows through time in GRU and make it powerful for sequence modeling. Update gate is responsible for deciding how much the past information should be carried forward to the current state, and it controls the balance between keeping the old memory and adding new information. So the mathematical formula used here is ZT equal to sigma of WZ into HT minus 1 into XT. Here HT minus 1 is the previous hidden state past memory, XT is the current input, and WZ is the weight matrix for the update gate, and sigma is the sigmoid function which outputs values between 0 and 1. If ZT is equal to 1, the model keeps most of the old memory. If ZT equal to 0, the model replaces old memory with new information. So, the input gate directly controls how much historical context is preserved in the network. Next one is reset gate. The reset gate controls how much of the past information should be forgotten or ignored when computing the new candidate state. So its formula is RT equal to sigma of WR into HT minus 1 into XT. Here WR is the weight matrix for the reset gate, The rest of the terms are similar to the update gate. So let's interpret its behavior. If RT equal to 0, the model ignores past information. So forgets the history. And if RT equal to 1 means the model fully uses past information. So the reset gate helps to decide how much past context is relevant for the current in computation. So together these two gates allow GRU to make intelligent decisions about memory. The update gate ZT controls how much memory to keep overall. The reset gate controls how much past information to ignore when forming new memory. This combination allows GRU to preserve important long-term dependencies and discard irrelevant past information and adapt dynamically to different sequence patterns. Working of GRU. GRU processes sequential data one step at a time using the current input and the previous hidden state to produce a new hidden state. Step 1. Take input and previous hidden state. At time step t, the GRU receives two input xt, ht minus 1. So xt is the current input and ht minus 1 is the previous hidden state, memory from past time step. These two together represents what is happening now and what has already been learned. Step 2. Compute update gate ZT. The first operation is to compute the update gate. This gate decides how much past information should be carried forward into the new state. It is calculated using both the current input and previous hidden state and produces a value between 0 and 1. If ZT is close to 1, the model keeps most of the old memory. If ZT is close to 0, the model relies more on new information. So, the update gate controls the balance between old and new information. Step 3. Compute reset gate RT. The GRU computes the reset gate. This gate decides how much past information should be ignored when forming the new candidate state. If RT is close to 0, the model forgets past information. If RT is close to 1, the model uses past information fully. So this helps the model selectively remove irrelevant history when needed. Next step is generate the candidate hidden state HT. Now the GRU creates a candidate hidden state written as HT. So this step combines current input XT, filtered past memory controlled by reset gate RT. The reset gate determines how much of the previous hidden state is used here. This candidate state represents a possible new memory based on current input and relevant past context. So next step is compute the final hidden state. Finally, the GRU computes the final hidden state. This step uses the update gate to combine previous hidden state and ht-1 and candidate hidden state ht. So the final memory is a weighted mix of old information, new information. If update gate is high, more old memory is kept. If update gate is low, more new memory is used. So GRU works like this. So it decides what to remember. It is an update gate and decide what to ignore. It done by reset gate and create a new possible memory done by candidate state and combining old and new memory to form the final step. These are the steps under GRU RNN. Let's see the advantages and disadvantages of GRU. Um, First, we will see the advantages. It is simpler than Lstm. One of the biggest advantage of GRU is its simpler architecture when compared to Lstm. GRU combines multiple gates into fewer components, which makes the overall structure less complex. This simplicity makes it easier to understand, implement and optimize. Second one, faster training. Because GRU has a simpler structure, it requires less computation per time step. This directly leads to faster training period, reduced computational cost, lower memory usage. So GRU are often preferred when training efficiency is important. So next one is fewer parameters. So GRU uses fewer parameters than Lstm since it has fewer gates and more compact design. So fewer parameters means it reduced risk of overfitting and faster convergence during training, more efficient model deployment, and this makes GRU suitable for systems with limited computational resources. And next one is good performance on many tasks. Despite being simpler, GRU performs very well in a wide range of sequence modeling tasks. It has been successfully used in speech recognition, time series forecasting, natural language processing, and in many cases it performs is comparable to compared to Lstm. So the main reason GRU is efficient is because it uses fewer gates and which reduces the number of computations needed at each time step, and it makes it computationally efficient without significantly sacrificing the performance. And next comes to disadvantage. It is less expressive than Lstm. So one limitation of GRU is that it is less expressive because GRU has a simpler structure and fewer gates. It has a less fine-grained control over memory compared to Lstm. So Lstm can separately control the input, forget and output, while GRU merges some of these operations, which reduces flexibility. Second one is it may not perform well for very complex tasks. So in very complex sequence modeling problems like GRU may sometimes underperform when compared to Lstm. This is because it has a fewer control mechanism. The parameters here used are very less, and it may struggle to capture extremely long or complex dependencies. So for a highly demanding task, Lstm is often preferred. So the main limitation of GRU comes from its simplicity. So while fewer gates, very less gates makes it efficient, they also reduce the level of control the model have over memory, making it slightly less powerful in very complex scenarios. Applications of gated recurrent unit. So first one is speech recognition. It is widely used in speech recognition systems where the goal is to convert spoken English into text, and speech is naturally sequential and each sound depends on previous sounds. So GRU helps the model understand these temporal relationship and accurately interpret spoken words. And second one is machine translation. So it is used in machine translation system where text from one language is converted into another language, translating English sentence into French or a Hindi, which requires understanding word order and context. So it helps to maintain the meaning of the sentence across languages by capturing sequential dependencies. And third one is text generation. So in this case, the GRU model are trained to predict the next word in a sequence. So by repeatedly predicting one word at a time, they can generate complete sentence, paragraph, or even stories. So next one is time series prediction. So it is highly effective in time series, so such as stock price prediction, weather prediction, sensor data analysis, etc. So since the time series data depends heavily on past values, the GRU can learn patterns and trends over time to make accurate predictions. So real life examples here is the weather is very the input is the weather is very dash. So the GRU model processes the words one by one. The updates the memory, weather updates the context, is updates meaning, very prepares prediction context, and finally based on all the previous words the model predicts the output hot. So in this example, the GRU uses its memory mechanism to understand the context of the sentence. So it does not just look at the word very, but also consider all the previous words in the sequence. So this allows it to make a meaningful prediction based on the full context, which demonstrating its strength in sequence understanding, language and modeling. So GRU is widely used in speech recognition, translation, text generation and time series predictions. So it is effective for any tasks involving sequential data, and it predicts outputs based on the previous context using memory states. So in real life applications, GRU helps models understand and generate meaningful sequences. Thank you.